Hello, future students and people who are missing right now. All right, so this is going to be the second half of lesson 4.7. I'm going to start just kind of recapping what we learned yesterday. So, yesterday we talked about acid base properties of salt solutions. So, like acetic acid. Is acetic acid strong acid? No. It's a weak acid. So if I have acetic acid and I react it with water, what do I get? Cool. And H3O plus. So acetic acid is an acid and its conjugate base is CH3COO minus, or the acetate ion. In this reaction, water is acting as the proton acceptor. So water accepts a proton and it's the base, and H3O plus is its conjugate acid. So acetic acid is our acid, and the acetate ion is its conjugate base. If I have something like sodium acetate, sodium acetate, this compound, it's a salt, which means, just an ionic compound. And I can dissolve sodium acetate in water. When I dissolve sodium acetate in water, I get two ions, the sodium ion and the acetate ion. And it turns out that these ions have the potential to change the pH of the solution when it's dissolved in water. In order to figure out whether or not a salt will change the pH of a solution when it's dissolved in water, I first have to figure out what ions it dissociates into. In this case, it's sodium and acetate. Then I have to look at each ion separately. The sodium ion. The first question I have to ask is, can that sodium ion act like an acid? Is it conjugate of a strong base? Remember that the conjugate of a strong base is a super, 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 super weak acid. So the conjugate of a strong base won't act as an acid at all. The question I ask is this the conjugate of a strong base? And I got a thumbs up. What conjugate or what base would this be the conjugate of? Anyone? So, yep, it's the conjugate of a strong base. Because it's the conjugate of a strong base, it won't affect pH. So sodium does nothing to the pH. But let's consider the other ion, the acetate ion. Now I have to ask, is this the conjugate of a strong acid? Well, take a second and think about this. This is a base. What would its conjugate acid be? Acetic acid. Is that a strong acid? It's not a strong acid. So the conjugate will affect pH. Let's write the equation to see how that works. CH3, COO minus, the acetate ion. When that reacts with water, I produce CH3, COOH, and OH minus. So this is acting as a base. It's accepting. So would a solution of sodium acetate be acidic, basic, or neutral? Basic. Okay. So if you missed yesterday's class, that's the briefest of introductions to what we did yesterday. I'll give you a second to finish writing this down. And I apologize to anyone who has to watch these videos because they are unedited and will have a lot of downtime. Still assuming they're better than nothing. Okay. So let's take this learning about the acid-base properties of salts and extend it to talk about titrations. Remember titrations from last year where your solution turned from clear to glow-in-the-dark pink because you added too much, but you were really aiming for that light pink color? So those were titrations. And when you're doing titration, you have to find the equivalence point. And in order to find the equivalence point, you have to use the right indicator. The ones you did last year, you likely used phenolphthalein, which goes from colorless to pink. It's pink when it becomes basic. It's colorless in acid. So the endpoint for that reaction was somewhere between 8 and 10. Different indicators have different endpoints. So we need to be able to estimate ahead of time what our endpoint will be before we do a titration. You don't have to have this list memorized. You'd always be able to look this up. But let's talk about titrations. In this reaction, I've got 20 milliliters of NH3 titrated against HCl. I want to know the pH at equivalence. What's my first step here? Every time, balanced chemical equation is your first step. What is that going to produce? Cl minus? All of these ions dissolved in solution? Ooh, pause for a second. Again. When we're titrating, we are starting with a concentration of 0.20 mole liter NH3 and 0.20 mole per liter HCl. My volume of NH3, I need to convert that to liters. It'll be 0.0200 liters. Do I know what volume of HCl I have or am going to use? No. That's what I'm trying to calculate. This is what I'm looking for. What can I find in step 2? Number of moles. Step 1, always balance the whole equation. Step 2, number of moles. So 0.2 times 0.02 is 0.004 moles. What's step 3? Mole ratio. What is my mole ratio? 1 to 1. So I'm just going to my 0.004 back in the table. I know that's 1 to 1 mole ratio of NH3 to HCl. How would I go about finding the volume of HCl I used? Concentration divided by moles. I know concentration is the number of moles per liter. So to find the volume, the number of moles divided by the concentration. So that means our volume will equal 0.0 divided by 0.20. What's the units for that? Liters. Excellent. Okay. Now, if this was grade 11 chemistry, we'd be done. Sadly, we're not done yet. What we really want to know is, are either of these ions going to affect pH? What this really formed, the NH3 plus the HCl, was ammonium chloride, a salt. And I need to know, can any of these ions affect pH? So I'm going to have to figure out if they affect pH and what their concentration is in order to figure out how much they affect pH by. Okay. So when we look at NH4+, is that the conjugate of a strong acid? Sorry, of a strong base? So will it affect pH? Yes. So NH4 plus and water can react together, like we saw, and form NH3 and H3O plus. So we know that that NH4 plus is going to make the solution acidic. Just because it formed NH4 plus, I know that it's going to be a little bit acidic. Chlorine ion. Is that going to change pH? No. Chlorine is the conjugate of a strong acid, which makes it a super, super, super weak base. Won't change pH. So it's not the chlorine I have to worry about, it is the ammonia. So I know it's going to be a little bit acidic, but I don't know how acidic. In order to figure out how acidic, I have to figure out what the concentration of that ammonia is. Eventually, I'll do that. But hold on a sec. What's my total volume now that I've mixed together 20 milliliters of NH3 and 20 milliliters of HCl? 40 milliliters. So my new volume is 0.0400. How many moles of the NH4 plus did I produce? What's the mole ratio? 1 to 1. So that means I also have 0.004 moles of that. So what's my concentration then? So this was step 5. Step 6, what's my concentration of NH4 plus? Is it? So get the concentration. I take the number of moles divided by the volume, so it's 0.1 moles per liter. Okay. So if that's 0.1 moles per liter, what do I have to do next? Oh no, not yet. That's the concentration of all the NH4 plus, not the concentration of the hydronium. I have to find the concentration of the hydronium ion. How am I going to go about doing that? Oof. Oh, yep, ice table. Remember, in question 5, we figured out that this is the reaction that's actually happening. NH4 plus H2O produces NH3 plus H3O plus. There's a plus there, I just can't draw it. Okay. So is this acting as an acid or a base? Acid, good. What's the initial concentration of my acid then? No. What's the concentration of my NH4 plus? 0.1. Don't care about the concentration of the water. What is my initial, before equilibrium happens, concentration of NH3? 0. What's my initial concentration of H3O plus? Okay. Is the concentration of NH4 plus going to increase or decrease? And the NH3 will increase by the same amount, and so will the concentration of the H3O plus. So at equilibrium, I can expect to have 0.1 minus X of NH4 plus, X of NH3, and X of H3O plus. This is what I want to know. That's how I'm going to figure out the pH. What do I need to get that? Yeah, how am I solving for X? What equation do I put it in? Cole? Not quite. Is this acting as an acid or a base? So Ka is equal to the concentration of NH3 times the concentration of H3O plus divided by the concentration of NH4 plus. So that's X squared over 0.10 minus X. But what's Ka? How would I find that? Back and and I have looked at this already. The back of the textbook tells me the value for Ka is 1.8 times 10 to the, no, I knew that didn't sound right. The value for Ka is 5.6 times 10 to the negative 10. Do I want to solve the quadratic formula? If you're keen, you can definitely solve the quadratic formula from this to solve for x. Go ahead. But to check to see if you don't have to solve the quadratic formula, you take the initial concentration and you divide it by Ka. If it's greater than 500, you can ignore the change. Will that be greater than 500? It will be greater than 500, which means I can ignore the change. So now, solving for x, 5.6 times 10 to the negative 10 times 0.1, and then I want the square root of that. And it's plus or minus 7.5 times 10 to the negative 6. Can I have a negative root? No. Question. The initial concentration, like the concentration of our NH4 plus, divided by Ka. Initial divided by your equilibrium constant or Ka value or Kb value, depending on which one of these you're solving. Okay. So x is equal to 7.5 times 10 to the negative 6. But am I just solving for x? No, x means something. I substitute x back into this table. So x tells me the concentration of H3O is 7.5 times 10 to the negative 6. What can I get once I know the concentration of H3O plus? The pH. Instead of, oh, because from the concentration of H3O plus, that's how we tell what pH is. So we also know, like, X is also equal to the concentration of the NH3, right? They're the same, but I don't care about the NH3 because I care about the pH right now, and that's why I'm. Yep, and you would be using Kb instead of Ka. Yes. I mean, if both of the ions affected pH, you'd have to consider both, see which one's bigger. Good time. Did anyone do the negative log of 7.5 times? 5 point, say that one more time. 5.1? Okay. Excellent. So 5.1 is our pH. And that makes sense. We know it should be a little bit acidic. We already looked at this ion and saw it's going to make an acid. And now we know exactly how acidic it's going to be. The question asks to select an appropriate indicator. How would I do that? Look at the chart. So if we go back a slide, and I look for something that changes color around a pH of 5, I can see that methyl red would do a pretty good job there. So obviously these problems are super simple and have very few steps. But even though they're so simple and have so few steps, maybe we'll try one more. No? Oh, I know. Okay. So this one, try all those grade 11 steps by yourself first. Write the balanced chemical equation, calculate the number of moles, and then do the mole ratio. And I'm going to try and make the text a little higher so that I have more space. And I recorded that too. So step 1, balanced chemical equation. Step 2, number of moles. Two products, salt and water. It's a neutralization reaction. I'm reacting an acid with a base, so I get a salt and water. Good point. Let's write the balanced chemical equation first. I know. So, my products will be sodium, benzoate, and the product water. It's a neutralization reaction. Um, okay. And I didn't write it down, but, and you wouldn't really need a volume, but it will feel more natural if I tell you we're working with 100 milliliters of the NaOH. So the concentration is 0.025 moles per liter, and my concentration is also 0.05 moles per liter. My volume of the NaOH would be 1 liters. My number of moles would be what I find next. So 0.025 times 0.1 gives me 0.0025 moles. What's my mole ratio? 1 to 1. So if I have this many moles of the NaOH, I know I have this many moles of the benzoic acid. And again, I would end up with the same number of moles of the sodium benzoate. How much of the CH5COOH do I need? I could solve using the C is equal to N over V formula, but I know it's all the same concentration, so it's also going to be 1 liter. But what I really need to know is what's the concentration of my salt? So what's the volume that the salt is dissolved in now? So I've got 100 milliliters and 100 milliliters and mixed together. I have 200 milliliters. So 0.0025 divided by 0.2. There's my concentration of the salt. So that's all the grade 11 mole ratio biochemical equation half of this. But now we have to think about the acid-base properties of salt solutions. So the sodium benzoate. We have to find out if that salt dissolved in water can affect pH. What two ions does that salt make? What does it split up into? Yeah, this thing. This thing. Okay. So these are the ions it splits up into. Let's consider the sodium first. Can that affect pH? But the other one, is that the conjugate of a strong acid? No. It can affect pH. If I react that with water, well, what do I get? And, okay. So this tells us, this OH minus, tells us that for sure the solution is going to be basic, right? Okay. What's my concentration of the sodium benzoate? So what's the mole ratio between the sodium benzoate and the sodium? 1 to 1. What's the ratio between the sodium benzoate and the benzoate? 1 to 1. So if my concentration of this 0.0125, my concentration of this will also be 0.0125. Pay attention to that step because sometimes it's not a 1 to 1 mole ratio. Sometimes it's a 1 to 2 mole ratio, and so on. Okay, so what do I do next? So I know that initially my concentration of this is 0.25. I don't care about the water. How much of the benzoic acid do I have to start with? 0. And the OH minus? Also 0. This is going to increase or decrease? an increase, and it's all by 1-to-1 mole ratios. Okay, but here, is the benzoic acid or the benzoate acting as an acid or a base? So do I need the base dissociation constant or the acid dissociation constant? Base. So I kind of ran out of room. I'm moving up over here. So Kb equals the concentration of benzoic acid times the concentration of OH minus divided by concentration of C6H5COO minus. So Kb equals x squared over 0.0125 minus x. Where do I get Kb? Back of the Ooh. I look in the back of the textbook though, and it doesn't have the value for Kb for benzoic acid or for benzoate. It does have the Ka for benzoic acid. So I know that Kw is equal to Ka for the conjugate times Kb. What is the value for Kw? The back of the textbook tells me that Ka for benzoic acid is 6.3 times 10 to the negative 5. Can I solve to find out what Kb is?
Wait, you're back? Okay. No?
Ooh, new seating plan though. I like this. Yes. Ah, this is great though. I like, look how focused you are. Are you learning? Amazing. And you picked a good one because I would almost guarantee this question or something very similar will be on the unit test. Got that? Okay, so now I know what the value is for Kb. If I plug this value back into my equation, would I have to solve the quadratic formula? Well, I should check because it'd be really nice not to solve the quadratic formula. Remember that test to see if you have to solve is the initial concentration divided by Kb. So that would be 0.0125 divided by 1.6 times 10 to the negative 10. Is that bigger than 500? Oh, doesn't matter at all. I think both are used commonly. The textbook, well, they seem to use both. So whatever case you like. So 0.0125 divided by that, please be over 500. Oh, way over 500. Excellent. So that means I get to ignore this here. And solve for x. So x is plus or minus 1.4 times 10 to the negative 6. Obviously, we can't have negative concentrations, so we have to use the positive root. That tells me that the concentration of the OH minus at equilibrium is 1.4 times 10 to the negative 6. What can I get from that information? I could get POH. I got 5.8. It's the negative log of the hydroxide concentration. No, it's like literally negative sign. Yeah, yeah. And what do we know about pH plus POH? So in case you missed that, pH plus POH is equal to 14. So if I know that POH is 5.8, pH is 14 minus 5.8, or 8.2. So the pH at equilibrium is 8.2. And there were only 500 steps to get to that answer. Okay. So yeah. But to get like 3 marks for grade 11 work, so that's useful. Okay. So I've got, all right, this question. Question 2, you definitely have time in the next 25 minutes to get through question 2 of the homework. There is an answer key posted for those who are watching this video online. And tomorrow we'll move on to lesson 4.8. You've got some time to do some practice right now. You know, definitely do this question before the unit test.